In today's lesson, we are mastering partial fraction decomposition. This technique allows us to break down complex rational functions into a sum of simpler fractions. For your Pure Mathematics 3 examination, this skill is absolutely fundamental, as it serves as a prerequisite for more advanced topics like integration and binomial expansions. You will learn to identify different types of denominators and apply the correct decomposition form to each. Before we decompose a fraction, we must ensure it is a proper rational function. A rational function p of x over q of x is considered proper if the degree of the numerator is strictly less than the degree of the denominator. If the degree of the numerator is greater than or equal to the degree of the denominator, it is an improper fraction. In such cases, you must first perform polynomial long division to extract the quotient and a proper remainder. For the 9709 syllabus, we focus on 3 primary cases of proper fractions based on the factors in the denominator. The first case occurs when the denominator consists of distinct, non-repeated linear factors. For every factor of the form ax plus b, we assign a partial fraction with a constant numerator capital A. In your exam, if you have 3 distinct factors, you simply add a third term with a constant capital C. The goal is to find the values of these constants that make the equation an identity, meaning it is true for all values of x. Think of it as decomposing a complex structure into its fundamental building blocks. Let's express 1 over the product of x minus 1 and x plus 2 in partial fractions. First, we set up the identity by assigning a constant to each linear factor. Next, we multiply the entire equation by the common denominator to clear the fractions. To find the constants a and b, the substitution method is often the most efficient. We choose values of x that make one of the terms 0. By letting x equal 1, the b term vanishes, allowing us to solve for a as 1/3. Now, let's eliminate the a term. With b found as negative 1/3, we can write our final result. Result: 1 over the product of x minus 1 and x plus 2 equals 1 over 3 times x minus 1 minus 1 over 3 times x plus 2. The graph on the right illustrates this decomposition. The red dashed line represents our original complex function, while the blue and black curves represent the simpler partial fractions we just found. Notice how they combine to create the original behavior. Today, we are discussing Case 2, repeated linear factors. The second case involves repeated linear factors. If a factor is squared, such as cx plus d squared, it must be represented by 2 separate terms in your decomposition, one with the linear power and one with the square. Here is the general form. For the expression p of x over a x plus b times cx plus d squared, we set it equal to a over ax plus b over cx plus d squared. It is a common mistake in exams to forget the linear term. You must include every power of the factor from 1 up to the highest power present in the denominator. If it were a cubic factor, you would need 3 terms. Let us look at an example. Let us express 2x plus 1 divided by x plus 1 multiplied by x minus 2 squared in partial fractions. Note how x minus 2 squared requires 2 separate terms. Here is our identity. Multiplying through by the common denominator gives us this linear equation. We use the substitution method for the roots. First, let x equal 2 to eliminate a and b. Next, let x equal negative 1 to eliminate b and c. To find b, we can compare coefficients of x squared. On the left, the coefficient is 0. On the right, x squared comes from a and b. Substituting our values back, we obtain the completed decomposition. Using coefficients is often faster than choosing a third value for x. The final case involves irreducible quadratic factors. These are factors like x squared plus 1 that cannot be factored into real linear terms. For such a factor in the denominator, the numerator of the corresponding partial fraction must be a linear expression, written as bx plus c. Here is the general form. When we have a proper fraction with a linear and a quadratic factor, we decompose it like this. In the Cambridge syllabus, students often forget to include the bx term and only write a constant. Remember, a quadratic denominator requires a linear numerator to account for all possible proper fractional components. Let us decompose 10 divided by the product of x plus 2 and x squared plus 1. We start by setting up our identity with a linear numerator over the quadratic factor. Now, multiply by the common denominator. First, let's use substitution to find a. We can eliminate the second term by letting x equal -2. Now that we have a, we can find b and c by equating coefficients. Let's look at the coefficients of x squared. There are no x squared terms on the left. Finally, let's equate the constant terms to find c. The constant on the left is 10. On the right, constants come from a times 1 and c times 2. This gives us our final decomposed form. Always double-check your signs when writing the final linear numerator. Let's apply these techniques to a Cambridge-style past paper question. The objective is to express the following rational function in partial fractions. First, identify the denominator types. We have a distinct linear factor, x plus 2, and an irreducible quadratic factor, x squared plus 1. We set up the identity by assigning a to the linear factor and bx plus c to the quadratic factor. Clear the denominators by multiplying the entire equation by the common denominator. To find a, substitute the root of the linear factor, x equals -2. Now, let's find b by equating the coefficients of x squared. Finally, let's find c by equating the constant terms. Substituting these values back gives us the final result. We can factor out 1/5 to make the final answer look much cleaner. This step-by-step approach ensures you don't lose marks for arithmetic errors. Let's look at some common mistakes to avoid in your exams. The most frequent error is neglecting the linear term in repeated linear factors. If you have x plus 1 squared, you must have terms for both the first power and the second power. Without both, the identity will not hold. For irreducible quadratic denominators, students often write just a constant b instead of bx plus c. Always check the degree of the denominator factor. If it is quadratic, the numerator must be linear. Many students jump straight into decomposition without checking the degrees. If the degree of the numerator is equal to or higher than the denominator, you must use polynomial long division first. Failing to do so will lead to incorrect values for your constants. Finally, watch out for arithmetic errors during substitution. When substituting negative values like x equals -2 into squared terms, ensure you treat the signs correctly. For example, -2 squared is +4, not -4. Now, let's look at some practical Cambridge examination tips for this topic. Tip 1. Always verify your decomposition by substituting a random value for x, like x equals 0, back into both sides of your identity. Tip 2. Clearly show the common denominator multiplication step. Examiners look for this to award method marks. Tip 3. If you encounter a large fraction in your result, recheck your simultaneous equations or substitutions immediately. Always use the identity symbol, which is 3 horizontal lines, when setting up your initial equation. This shows the examiner you understand that the relationship holds for all values of x, not just specific solutions. To save time, always prioritize the substitution method for linear factors. It directly isolates constants and reduces the complexity of the simultaneous equations you need to solve. After finding your constants, a very quick way to verify your work is to substitute x equals 0 into both sides of your identity. If the results match, your decomposition is likely correct. When your constants are fractions, like a equals 1/3, do not leave them in the numerator. Write the denominator of the constant in front of the bracket in the main denominator, such as 1/3 times the quantity x minus 1. This is the standard expected in the mark scheme. Remember that partial fractions are often the first part of a multi-part question. Always ensure your decomposition is correct, as an error here will often lead to incorrect results in subsequent integration or binomial expansion steps.